Okay, thank you for your questions. So our team is actively exploring several frontier areas in energy storage and electrocatalysis, with two current priorities. First is next generation battery electromaterials. We focus on phosphorus-based anode and molybdenum disulfide (MOS2) derived cathode holes to improve energy density, charge discharge rate, and long-term cycling. The second is interface and defect engineering in electrochemical energy system. We employ strategies like electrolyte engineering, atomic doping, and defect vacancy modulations to enhance cycling stability and kinetics at electrolyte boundaries. Our recent representative works, the first one is fast charging phosphorus anode with forinate weakly sulfate electrolytes, published in Advanced Materials, May 2025. This work introduced forinate weakly sulfate electrolytes that regulate the solvation shield around phosphorus anode. This design enable fast charging capability and greatly improve cycling stabilities. The phosphorus-based anode delivered an ultra-high capacity of 2,615 capacities at 1C and maintain more than 91% retentions after 1,000 cycling. Even at 4C, it retained 96.7% after 1,500 cycles. Another work is indium dope inner layer molybdenum disulfides for enhanced sulfur redox kinetics, published in Advanced Materials, June 2025. This research demonstrates that doping indium into inner layers of MOS2 stabilize sulfide vacancy framework, enabling significantly enhanced performance in lithium sulfide batteries. This work revealed a strong defect doping synergy, where indium incorporations lowers surface energy and stabilize high activity sulfide vacancy sites. As a result, the lithium sulfide batteries achieve high performance, 1,000 capacity after 100 cycle at 0.5 C and maintain stability even under demanding conditions such as 5C rate, 8.7 milligram per centimeter square sulfur loaded. The mechanistic study further showed that indium doping enhanced sulfur polysulfide absorptions and reduce the energy barrier for lithium sulfide formations. Recent advances in potassium-ion battery, thin-air batteries, and flexible supercapacitors show strong potential for renewable energy storage system. However, several key challenges remain in improving energy density, cycle stability, and cost control. For potassium-ion batteries face issues with anode dendrite formations, large volume expansions, and unstable solid electrolyte interface. The larger K potassium ions also limit suitable cathode materials and reduce structural stabilities. For thin-air batteries, suffer from poor reversibility due to thin dendrites, side reactions such as hydrogen effluent reactions, and catalyst degradations. The oxygen reduction reactions and oxygen effluent reactions kinetics remain sluggish, and air electrodes stability is limited by carbon dioxide induced carbonate formation in alkaline electrolytes. And for flexible supercapacitors, their low energy density is a core limitations. Um, Certainly, pseudo-capacitive material boost capacitors. However, they may lack mechanical durability and are costly. So therefore, in this case, rational material designs and interface optimization could be the solutions to solve those challenges. Okay, in my research, I mainly employ a combination of material designs, composite fabrications, and surface engineering to enhance the electrochemical performance of electromaterials. For example, in material designs, our recent work of inner layer indium doping MOS2 achieve highly stable sulfur vacancy for lithium sulfur battery. In this study, the lithium atom are precisely doped into the inner layer of MOS2, stabilizing the sulfur vacancy and lowering the material surface energies. For composite fabrications, our recent work of multi-component anode based on amorphous zinc phosphide for fast charging discharging lithium-ion battery, published in Advanced Energy Material. And in this approach, we develop a one-step ball milled amorphous composite material, such as zinc phosphides with in situ form zinc phosphate, and also with the carbon. And the phosphorus, the porous composites enable excellent lithium access and rapid kinetics and structural integrity. So the result is the device amorphous porous anode achieve 985 capacities over 2,200 cycles at 3C, and even at 12C, the sample sustained 600 capacity after 2007 cycles. And for structure surface engineering, our recent work on fast charging phosphorus anode enabled by 4-way weakly sulfate electrolytes published in Advanced Materials. Instead of coating the electrode itself, this work engineered the electrolyte interface by using a 4-way weakly sulfate electrolytes. This electrolyte design suppressed the polysulfide dissolutions, stabilize the SCI formations, and accelerate the lithium storage kinetics. The phosphorus-based anode deliver an ultra-high capacities of 2,615 capacities at 1C and maintain more than 91% retention after 1,000 cycling. And even at 4C, it retained 96.7% after 1,500 cycles. So I believe the strategy I employ are directly aligned with the increasing demand of future smart energy storage device. As energy system move towards flexible, variable, and multifunctional format, material system must meet more than just electrochemical performance. They must also be lightweight, mechanically robust, and compatible with miniatures architectures. So therefore, I see this kind of potential. For example, those approaches can contribute to integrate energy system, and such as the self-power sensor, smart texture, or on-chip energy storage that require not only high performance, but also form factor adaptability and multifunctionality. So sustainability is becoming a central pillar in energy storage research. Over the next decade, I believe The most impactful breakthrough will come from three key areas. First, abundant and low toxicity materials. The shift towards earth-abundant elements such as potassium, zinc, sodium, and iron offers a clear path to sustainability and scalable, low-cost, environmental friendly storage. The second one is green electrolyte and binder. The development of bio-derived or water-based electrolytes and polymer binders will reduce the reliance on toxic solvent and foreign components. So electrolyte design for recyclability, reduce volatility, and low environmental impact are especially promising for large-scale and wearable applications. And finally, the recyclability and biodegradable component would be the next area. Designing electro materials and separator that are recyclable or even biodegradable can significantly reduce the cost. And so therefore, in my view, integrating this sustainable material with high performance architectures through smart design, low energy synthesis, and modular recycling will be crucial for next generation's high efficiency energy storage system. Smart material research is rapidly expanding, and I see the key growth area in multifunctional system, AI guide material designs, and sustainable smart materials that align with environmental goals. These directions are critical for the advancing application in soft robotics, wearables, and biomedical devices. So for the journal futures, I suggest strengthening its role as an interdisciplinary platform, highlighting work that bridge functional science with highlighting the work and bridge fundamental science with real-world impact, incorporating invite perspective or topical reviews, especially from emerging researchers, can enhance diversity and through leadership. Maintaining high review standards and emphasizing technological reference will be essential for the continued growth and visibility of the journal. I value curiosity, resilience, and strong sense of ownership in young researchers. So these qualities drive independent thinking and sustained progress. To keep their enthusiasm alive, I encourage them to explore bold ideas, connect their work to real-world challenge, and celebrate small wins. So I also foster an open, collaborative environment where questioning is welcome and failure is seen as a part of discovery. So most importantly, I help them see the bigger pictures, how their work contributes to advancing knowledge and making a tangible impact. Thank you.